Co-21A, day 2. Today's the 9th of June. Let's get that cursor out of the way. All right, where to begin? So, I saw people said they would love to see some things about, or I wrote some notes down here somewhere. Somewhere, yeah. The unit circle, logarithmic functions, trig functions, inverse operations, which I took to mean inverse functions, I believe. So a lot of things to talk about, but we can definitely cover it. So let's talk about the unit circle to start with. So here's what I would say as far as unit circle goes. The whole idea here, this is, sorry, I just don't, writing here, there's like a little like bar right here that's really in my way, but I don't think my paper wants to stay. Oh, we can try that. Okay. Sorry, 1 second, small adjustment. Okay, we'll see how this works. So the unit circle of radius 1. I usually like to label these 4 points, although there are certainly more points that you could label on the unit circle. The idea is that starting from the positive x-axis, if you think the correct word here is subtend, but I should say go. If you go an angle of theta counterclockwise, then the point on the unit circle here is having an x coordinate that is cosine of that angle and a y coordinate that is sine of that angle. I have never been one to memorize the unit circle, right? It just doesn't work for me. It's not my jam. On the other hand, what I do like to do is remember some right angle trigonometry, which is that in a triangle, a right triangle, I should say, where you're calling one of the acute angles theta, you can call this other one whatever you want. And if you label these sides, I'm going to label them, I could go, yeah, let's go this way. The adjacent side, the opposite side, and the hypotenuse side. Then we can define the trig functions as sine of that angle is the opposite over the hypotenuse. Cosine of angle theta is the adjacent over the hypotenuse. And tangent of theta is equal to the opposite over the adjacent, which notably ends up being equal to sine divided by cosine. Because if you take this divided by that, you'll get the hypotenuses canceling and you'll get the opposite of the adjacent. I'll point out that tangent of theta is equal to sine of theta over cosine of theta. And then we have the other 3 trigonometric functions, the reciprocal functions. The reciprocal of sine is cosecant of theta. It's the hypotenuse divided by the opposite. The reciprocal of cosine is secant of theta. That's the hypotenuse divided by the adjacent. And finally, the reciprocal of tangent is cotangent of theta. It's the adjacent divided by the opposite. It is also notably equal to cosine divided by sine. So at some point, we're probably going to need to find trigonometric functions of particular angles. Or really often it's actually the other way around. You have to be able to find the inverse trig function of a certain geometry. So we'll kind of talk about both those things from here. You can think of this in the unit circle way, or you can think of it in the triangle sort of way. We'll kind of talk about both for a second. So there's 2 triangles you might want to be aware of. One is the favorite 45, 45, 90-degree triangle. It's also called an isosceles right triangle. And we often kind of think about creating it by taking a square whose sides are all length 1 and then cutting it in half diagonally so that you get a 90-degree angle there and 45-degree angles there. So if we look at this square, sorry, this triangle, we don't really care about this part over here. We have a side length of 1, side length of 1, And then to find the hypotenuse length, we're going to use the Pythagorean theorem. As a reminder, Pythagorean theorem says in the right triangle, the sum of the squares of the legs is equal to the square of the hypotenuse. So in this case, we would say that a squared plus b squared is equal to c squared. In this triangle, we're trying to find the length of the hypotenuse. I'm going to call it c. So we get 1 squared plus 1 squared equal to c squared, which means that 2 is equal to c squared, or c is equal to the square root of 2. Now that we have all sides of this triangle, we can find or evaluate the trigonometric functions of the 45-degree angle. But typically, we usually try to, I prefer is not the right word, but usually in calculus, we try to use radians instead of degrees because it's just more typical. Radians don't have a dimension or a unit, whereas degrees kind of do. So we're going to do this in terms of radians instead of degrees. So instead of 45 degrees, I'm going to try and stay on the screen there. So 45 degrees, we're going to multiply that by pi over 180 to convert it to radians. That's going to be 45 pi over 180, which reduces down to 9 pi over 36, which reduces down to pi over 4. So 45 degrees, pi over 4 radians. So now looking at this triangle, we're going to evaluate sine of 45 degrees and get 1 over root 2, which we could rationalize and should rationalize probably as root 2 divided by 2. By multiplying the top and bottom by whatever radicals in the denominator there. So root 2 times root 2 is just 2 because it's the square root of 4. And then the top is root 2. My favorite thing about 40, I said radians and I wrote degrees. It's okay. They're interchangeable. So I'm going to write cosine of pi over 4. My favorite fact about the angle pi over 4 is that sine and cosine have the same value. It makes it easy to remember what's what. So cosine of pi over 4 radians is also going to be 1 divided by root 2. It's the adjacent divided by the hypotenuse, which is the exact same value. And then tangent of 45 degrees or pi over 4 radians is the opposite over the adjacent, which is 1 over 1, which is 1. I would say we're talking about like evaluating trig functions at a particular angle. We often limit ourselves to just the primary trig functions here and not the reciprocal ones. Because if you know these first 3, then you kind of by default know the other 3. We know that cosecant of pi over 4 is going to be the reciprocal of sine of pi over 4. So it's going to be root 2 divided by 1, which is just root 2. Secant of pi over 4, which is the reciprocal of cosine, is going to be also root 2. And cotangent of pi over 4, which is the reciprocal of tangent, is going to be 1 over 1, which is 1. So you'll frequently see people kind of leaving these 3 off if they've already found these 3 because you kind of just assume, oh yeah, we know how to get the other 3 if we know these first 3. So that's one of the triangles I like to be familiar with when I'm talking about evaluating trig functions. There's another triangle that's also very useful. It's the 30, 60, 90 triangle. Again, also, if I ever get like, if I do this and you're like, James, I can't see what you're writing, just let me know. And I said this last time, but there's a few new people, so let me know if I'm getting off camera. The other triangle we use in trigonometry is, well, I'm going to start with an equilateral triangle. As best I can draw it. So equilateral triangle, I'm going to make all the side lengths 2 because it's convenient. And then just like with the square, I'm going to cut it in half in a useful way. I'm going to cut it in half down the middle. This angle is 60 degrees. This angle is 60 degrees. And this angle up here was 60 degrees, but I cut it in half. So now that angle there is 30 degrees. So here's my 30, 60, 90 right triangle with a hypotenuse of length 2, a base of length half of 2, and a height that we have to find. I don't really care what I call it. I'm going to call it x. I'm going to solve for x, again, using the Pythagorean theorem. 1 squared plus x squared equals 2 squared. So x squared is equal to 4 minus 1, which is 3. So x is equal to the square root of 3. I'll point out, just in general, if I was just solving this equation, I would actually get 2 solutions. I'd get x equal to positive root 3 and negative root 3. But since I'm finding the length of a side of a triangle or a thing, x should be positive here. So it doesn't make sense to write both solutions, although you should be aware that there would be 2 solutions in general. And so we can use this triangle to find the sine and the trig values of both the 30-degree angle and 30 degrees times pi over 180 degrees is equal to 30 pi over 180, which reduces to pi over 6, and 60 degrees. And 60 degrees is twice 30 degrees, so it should be 2 pi over 6, which is pi over 3. So these I would kind of classify or label these 3 angles, pi over 4 or 45 degrees, pi over 6 or 30 degrees, and pi over 3 or 60 degrees. It's kind of like the main angles you should know how to find sine, cosine, tangent, and the reciprocal functions of. It doesn't come up like all the time, but it comes with enough that you do need to know how to evaluate them or how to figure out what they evaluate to. So let's look at these relatively quickly, and then we'll kind of circle back around, to the unit circle. That's terrible. So let's look at this triangle kind of oriented as is, although you really don't care which way you're drawing it. If I'm going to find sine of pi over 3, well, that's 60 degrees. So I'm going to say it's the opposite over the hypotenuse, which is root 3 over 2. Cosine of pi over 3 is the adjacent over the hypotenuse, which is 1 over 2. And tangent of pi over 3. I could look at the triangle and say, okay, it's opposite over adjacent, which is root 3 over 1. But I can also look at sine over cosine and say, oh, well, sine root 3 over 2 divided by cosine 1/2 ends up exactly being, well, the 2's end up canceling, right? If you flip and multiply, the 2's cancel, and you just get root 3 over 1, which is root 3. Yes, of course. I feel like, let's see if I can move this to the side a little bit here. There we go. There we go. Much better. Okay. And then we could find the reciprocal functions. I know I said we should just omit it, but obviously I'm not. So cosecant of pi over 3 is 2 over root 3. And if we multiply by root 3 over root 3, we're going to get 2 root 3 over 3. Secant of pi over 3 is 2 divided by 1, which is 2. And cotangent of pi over 3 is 1 over root 3. If we rationalize that, we get root 3 over 3. And then, sure, we might as well finish off our list here. We'll use the same triangle to find the trig functions of pi over 6 radians. So now we're looking at this angle, which is equal to pi over 6, instead of this angle, which is equal to pi over 3. So we still have the same values, but the role of the opposite side and the adjacent side have interchanged. And if that's hard to see, I can also zoom in for a moment there. Yeah, if something is hard to see, I know my writing is not excellent. I'm not offended. You'd be like, hey, James, what does that say? Is a fine thing to ask. Or can you zoom in? Also a fine thing. Yeah, what's up?
So is cosecant opposite of sine?
I would use the different word. I would say it's the reciprocal sign. It's the flip. Opposite is usually a word I reserve for the negative of something. So I would say that 5 and negative 5 are opposites. 5 and 1/5 are reciprocals. So this is definitely, cosecant is the reciprocal of sine. In fact, we'll write down the quotient identities for trig functions in a minute here. So same deal over here. We're going to get actually the same exact value showing up. They're just going to be for different functions. So if we're going to try and find over here, say sine of pi over 6, well, now I'm looking at the angle pi over 6. I'm saying it's the opposite over the hypotenuse, which is 1/2. And cosine of pi over 6 is the adjacent over the hypotenuse, which is root 3 over 2. I always imagine or think of these two values going together. So whether your angle is 60 degrees or 30 degrees or pi over 6 or pi over 3, sine and cosine, one of them is going to be 1/2 and one of them is going to be root 3 over 2. And you kind of have to figure out which one is which. And then tangent of pi over 6 is going to be the reciprocal of what it was, right? Tangent of pi over 6 is going to be the opposite over adjacent, which is 1 over root 3, which rationalizes to root 3 over 3. And then the rest of them, cosecant of pi over 6 is equal to 2 over 1. Secant of pi over 6 is equal to 2 over root 3, which we rationalize as 2 root 3 over 3. You can't see that, sorry. That's a prime opportunity to be, hey, James, I can't see what you're writing. And then finally, cotangent to pi over 6 is going to be the reciprocal of, sorry, I'm just going to look at the reciprocal of tangent, which is 3 over root 3, which is root 3. Something worthwhile, in case you didn't know, any number divided by its own square root is equal to its own square root, right? 5 divided by the square root of 5 is the square root of 5. Checks out. Okay. Let me zoom back out before I get too crazy here. It's a manual zoom. What's that? Focus here. Those are the trig values I think you need to most be aware of. Now, they're not the only angles we can take trigonometric functions of. And I'm trying to think about the best way I would describe how to do the rest. Yeah, so 2 things I'll say. That's not true. I'm missing a lot of things. The 2 next things I will say is there's a really kind of slick way of memorizing the values of sine and cosine for the first 5 angles that occur on the unit circle. So let me show you that, because I think it'll make it easier if you feel like you need to memorize these. So back to the unit circle for a second. Really just looking at the first quadrant of the unit circle. So
Do you think you can move the
yes, I can. Sorry. It's a little challenging. So let's see, we've got let's use a different color here. Let's use lots of different colors. So here's my 45-degree angle, cutting it right in half. And that's a pi over 4 radians. And then we also have the smaller angle, pi over 6, which is 30 degrees. And then we have the larger angle, pi over 3, which is 60 degrees. We also have, at the beginning, on the x-axis, an angle of 0. And over here, 90 degrees, or pi over 2. And we know all 5 of these coordinates that are on the unit circle, right? The unit circle whose radius is what? 1, right? 1 literally means unit. That is why we call it a unit circle, because the unit is the name of the smallest kind of counting integer that we have. 1's the only positive number that isn't prime or composite. Right? Prime number like 7, it's got 2 factors. The composite number like 12 has more than 2 factors, but 1 only has itself as a factor if you're ignoring the negative numbers, which we should do. So this coordinate here is 1, 0. The coordinate for pi over 6 is the cosine value and the sine value. So let me ask you, looking at this angle here, I know we just wrote them all down. I don't remember which one's which. I know it should be a root 3 over 2 and a 1 over 2, but which one is bigger here? Is the cosine x coordinate larger, or is the sine y coordinate larger? The x, I've gone further right than I have gone up. I'm also below the line y equals x. So here the coordinates are root 3 over 2, comma 1/2. Here they're lovely, they're the same, they're both root 2 over 2. And then over here they flipped from root 3 over 2, comma 1/2 to 1/2, comma root 3 over 2. Lastly, up at the top here, the coordinate is 0, 1. Honestly, this is what I would do if I was trying to. And then I remind myself that the x, y coordinate is cosine first, sine second. If you're ever unsure, it's alphabetical. X comes before Y, cosine comes before sine alphabetically. If you don't like this, fine. Here's another way to memorize them. Make a chart. Let's see. What do we want to do in this chart? So I'm going to have my angle going across from the right, and then I'm going to have, let's do sine first. Yeah, sine first, and then cosine second. And leave some space down below for tangent as well. We're going to slip tangent in there. So my angle could be 0 radians or increasing pi over 6, pi over 4, pi over 3, pi over 2. I'm not just going to write this down. I'm going to kind of write it down. So here's what I'm actually going to do. I'm going to write the square root of something over 2. Yeah. In each of these spots. For sine and for cosine. Which might look moderately annoying. But I promise you it's only slightly annoying. Don't do it for tangent. All right, so check this out. So sine starts at 0 and then gets bigger, right? So I'm about to fill it in, just a second. So I'm going to write 0, 1, 2, 3, 4. Check it out. Square root of 0 is 0. 0 divided by 2 is 0. Sine of 0 is 0. Check. Square root of 1 over 2 is 1 over 2. Sine of pi over 6 is 1 over 2. Square root of 2 over 2. Yep. Sine of pi over 4 is square root of 2 over 2. Sine of pi over 3 is square root of 3 over 2. And sine of pi over 2 is the square root of 4 over 2, which is 2 over 2, which is 1. Kind of great. And then for cosine, it's backwards. 4, 3, 2, 1, 0. This really works for some people. I think it's super neat personally. There's also like this finger thing people do where like you do like cosine of like you kind of make, let me do it this way. So like my pinky finger is like the 0 degree or 0 radian angle. And my thumb is like the 90-degree angle. And then you go like, okay, I'm gonna do like sine of pi over 3. So I go up to like this one here, and then it's root 3 over 2. Or if I did sine of pi over 6, it'd be 1 over 2. And cosine's the other fingers. I have never liked that personally, but some people really like it, so take your pick. And then if you want to find so I should point out, you would never leave these like this, right? I'm not going to write the square root of 0 over 2 as my answer. If someone says sine of 0, that seems silly. I'm going to write 0. I'm going to write 1/2. These two stays are, I'm going to write 1. Same deal here. This is 1. This is 1/2. This is 0. And then, as I mentioned before, tangent of theta is sine of theta divided by cosine of theta. So tangent of 0 is 0 divided by 1. Tangent of pi over 6 is 1/2 over root 3 over 2, which becomes 1 over root 3. I'm not going to rationalize it because we don't have room. Clearly, root 2 over 2 divided by root 2 over 2 is something divided by itself, which is always 1. Not always 1. When is something divided by itself not equal to 1? When it's 0 divided by 0. 0 divided by 0, definitely not necessarily 1. It could be 1. It could also be 17. In fact, a lot of this class is going to be dealing with what happens when you get 0 divided by 0. So that's why I want to point it out, is that 0 divided by 0 could potentially end up being 1, but most of the time it could be anything. And then over here, root 3 over 2 over 1/2 simplifies to root 3. And finally, 1 divided by 0 is a problem. It's undefined. And then, so that was the first thing I wanted to say. The other thing I want to say is, for other angles, I typically employ this method. So for example, if I wanted to find, say, sine of, sure, 4 pi over 3. We have to do two things. We have to identify what's called the reference angle, which is the angle you would get if you measured this angle to the closest x-axis, which means we have to kind of draw the thing, or at least know where it lives. So 4 pi over 3 is a little bit bigger than pi. I should probably back up for just one moment and say, I've been talking about radians, like everyone's super cool with what a radian is. Let me slow down for a second and talk about what a radian is for just a moment. So Yeah, so many pens in the way here. So if you go all around the circle, unit circle or not, could be of any radius, the degrees you have traversed are 360 degrees. Right, you started at 0 degrees, you go all the way around, that's a 360 degree revolution, I guess. I don't know. I have the words, whatever. Or you could measure this in radians. What is a radian, you might ask? It is the angle you get that looks terrible. It's the angle you get, and I've drawn it approximately here, when the arc length on the circle is exactly 1 radius long. So what's the circumference for the equation, or what's the circumference equation for a circle? Circumference is 2 pi. Oh, sorry, you can't see that. Apologies. The circumference is 2 pi times the radius. So that means that this whole length around the circle is 2 pi radiuses long. Radii is the right way to say that. It's 2 pi radii long, which means the angle for one full revolution is exactly 2 pi radians. So 360 degrees is equal to 2 pi. We usually don't write the units for radians. We usually just write a number and leave it at that. But I could write radians. Which means that half a revolution, 180 degrees, is the same as pi radians. So that's what I've been doing when I've been changing from degrees to radians. I've been multiplying by a conversion factor, pi over 180, just like multiplying, 36 inches by 1 foot over 12 inches to convert from inches to feet. Same kind of idea there to get into radians. So all that to say, if I want to know what quadrant this angle ends up in, I'm seeing that that's a whole pi plus another third of a pi. So 1 whole pi is halfway around the circle, and then another third of a pi is like a 60-degree angle. So this angle that I'm thinking about here is going to land in quadrant 3. And then what I actually really care about is what we call the reference angle. The angle measured to the nearest x-axis. So if you're in quadrant 2 or quadrant 3, you're measuring back to the x-axis on the left side here. If you're in quadrant 4, or I guess quadrant 1, although you don't really need to for quadrant 1, you're measuring to the x-axis on the positive side here. So this is my reference angle. And that angle is the difference between 4 pi over 3 and the angle you get if you go halfway around the circle, which is pi. And that difference, 4 pi over 3 minus pi, is 4 pi over 3 minus 3 pi over 3, which is pi over 3. Oops, sorry. That's one thing we have to do is find the reference angle. The other thing we have to do is think about whether our trigonometric function is going to be positive or negative in the quadrant we have landed in. So I'll remind you, by looking back at the previous page, previous 2 pages, the first page, that the cosine value is the x-coordinate on the unit circle, and the sine value is the y-coordinate. So if we're in the first quadrant, x and y are both positive. So over here in quadrant 1, all trig functions are positive. Over here in quadrant 2, the y values are still positive, but the x values are now negative. So sine ends up being positive, and the other 2 prime trig functions, tangent and cosine, end up being negative. So here, sine is positive. It's quadrant 1, quadrant 2, quadrant 3, quadrant 4. Over here in quadrant 3, x and y are both negative, so sine and cosine are both going to be negative, but tangent, which is the quotient of x and y, or I should say y divided by x, is going to be positive. So over here in quadrant 3, tangent is positive. And lastly, in quadrant 4, well, the x values are positive, but the y values are negative. So over here, cosine is going to be positive. There's a mnemonic device people often utilize. It's all students take calculus to remember in which quadrant which trig functions are positive. You will notice I'm not mentioning the reciprocal functions. I didn't say anything about secant, cosecant, or cotangent. Let me ask you all, what's the reciprocal of positive 2? Is it still positive? How about the reciprocal of negative 3? Still negative. So if your original trig function was positive, its reciprocal is also positive. If your original function was negative, your reciprocal function is still negative. So if sine is positive, so is cosecant. And if cosine and tangent are negative over here, so are secant and cotangent. So back to where we were. So then in quadrant 3 over here, sine is going to be negative. I know that sine of pi over 3 is root 3 over 2. So sine of 4 pi over 3 is going to be negative root 3 over 2. And I know it's going to have the same value up to being different by a sign because of the symmetry of the circle, right? If I look over here, you kind of flip that. Sorry. The symmetry would have been nice to see right here. But the idea here basically is that, let's go big. So this angle here, pi over 3, the x coordinate is 1/2, the y coordinate is root 3 over 2. If I go over here, where my reference angle is pi over 3, and my actual angle is 2 pi over 3, the x and y coordinates are the same, except one of them is now negative, right? I still have the same kind of, I've gone the same amount up, over and up. It's just I've gone left instead of right. But I've still gone up. So this coordinate is negative 1/2 comma root 3 over 2. And if I go down here to an angle that's not pi over 3, not 2 pi over 3, not 3 pi over 3, but 4 pi over 3, where again, the reference angle is still pi over 3. This coordinate here is, well, now both x, not sine, and y have negative values. But they're all the same because we're just bouncing back and forth between here, there, down, and then over here to finish it off. You're at 5 pi over 3. Whoop, that looks not as nice as I wanted it to. Where a reference angle is still pi over 3. This coordinate is positive 1/2 comma negative root 3 over 2. So some people, not me, like to memorize the whole first quadrant of the unit circle and then just kind of fill in the other 3 quadrants by symmetry and then putting in the right signs. I prefer just to see what quadrant my angle lives in and then find the reference angle and then know the first quadrant value and then change the sign if necessary to be the right value. Along that same sort of thought process, if I wanted to find, say, the way to move the paper, if I was trying to find something like secant of, I don't know, 5 pi over 6, I never know what secant is. Like, it's just not something I know ever. So I'm always going to think of the reciprocal function first. Okay, I know secant is the reciprocal of cosine. So I'm going to say cosine of 5 pi over 6, just a little bit less than pi, lands in quadrant 2 because we're not quite all the way to pi. So we're looking something like this. There's my 5 pi over 6 angle. There's pi. How much do I need to get from 5 pi over 6 to a whole pi? Pi over 6. Kind of useful piece of information here. Almost any normal angle written in radians, the reference angle is usually just whatever pi over the original denominator is. So 5 pi over 6, the reference angle is pi over 6. 7 pi over 6, the reference angle is pi over 6. All those angles in the previous thing we just did, all these angles, pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3, all have a reference angle of pi over 3. That is not a coincidence. That is by design. Well, it's not really by design. It's kind of a feature of divisibility, but it's nice, is what's really the truth. So here, I know that cosine of pi over 6 is, let's see, that's the lesser angle, which is the bigger x value, so it's also root 3 over 2. Secant of pi over 6 is the reciprocal of that, which is 2 over root 3, which is 2 times root 3 over 3. And then finally, secant of 5 pi over 6. Again, I don't think you need to write all this. I'm writing it to show you the thought process here. Secant of 5 pi over 6 is going to be negative 2 root 3 over 3 because we're in the quadrant where sine is positive and tangent and cotangent are negative. Sorry, tangent and cosine. All that to say, eventually, you might be asked to evaluate some inverse trigonometric functions as well. So an inverse trigonometric function, literally, and I should say, actually, I should maybe talk about inverse functions before I just jump into inverse trig functions. So let's actually do that instead. So we'll circle back around to inverse trig functions after we talk about inverse functions for a minute. I feel like there's something else I want to say about trigonometry now. Oh, I know what it was. There were two more things I wanted to say about trigonometry. Some important identities. Yes, I mentioned the quotient identities. So there are some identities we should know. So here are some ones I already mentioned. Quotient identities. Quotient is another word for fraction. So we have the usuals. We have tangent equal to sine over cosine. We have cotangent equal to cosine of theta over sine of theta. You really should say the of whatever sine or cosine of. If you don't write the theta or the x or whatever the argument is, it really doesn't make sense. We also have that secant of theta is equal to 1 over cosine of theta. And we have that cosecant of theta is equal to the reciprocal of sine of theta. Those are not the only ones. You could also say that sine of theta is 1 over cosecant of theta, and cosine of theta is 1 over secant of theta, but you don't really need to write those down as well. And then after those, there are kind of my favorites. Favorites, maybe not the right word. The Pythagorean trig identities. So these really do stem from how the unit circle works and the Pythagorean theorem. So if you're thinking about, again, this point on the unit circle, if we drop this perpendicular here, and you call, right, this side x and this side y and this side 1, because it's a unit circle, and this coordinate is x comma y, but it's also cosine of your angle comma sine of your angle, then it's correct to say, well, x squared plus y squared equals 1 squared, which is just 1. But then x is really cosine, y is really sine, so cosine squared theta plus sine squared theta is equal to 1. I often refer to this as the most famous trig identity because it's the one that's kind of like, if someone said name one trig identity, this would be it. That'd be the first one I would ever think of anytime. And it does come up frequently. There are two, well, I should say, there's two other versions of this. You can isolate either sine squared or cosine squared. You can say sine squared equals 1 minus cosine squared, or cosine squared equals 1 minus sine squared. That does come up pretty frequently in this class. And then there's two other versions of this formula you can get by dividing the whole thing by either sine squared or cosine squared. So if we divide everything by cosine squared, I get cosine squared theta over cosine squared theta plus sine squared theta over cosine squared theta equal to 1 over cosine squared theta. We're going to simplify this. Cosine squared divided by cosine squared is 1. Sine divided by cosine is tangent, so sine squared theta divided by cosine squared theta is tangent squared theta. And 1 divided by cosine squared theta is secant squared theta. In my mind, this trig identity is unforgettable because once upon a time, a student told me, oh yeah, it's just I tan and get sexy. And immediately I could never forget it, even if I wanted to, which I kind of did, but I can't. So yeah, 1 plus tangent squared equals secant squared. I tan and get sexy. The other one is not as easy to remember. If you divide everything by sine squared, you're going to get cosine squared divided by sine squared, which is cotangent squared. Sine squared divided by sine squared, which is 1. And 1 divided by sine squared, which is cosecant squared. We usually don't write it this way. We usually write it as 1 plus cotangent squared theta equals cosecant squared theta. When I met the student who came up with this lovely gem, I can't get sexy, I was teaching at UCCS, which is in Colorado Springs, Colorado. And so my students came up with, I sleep on a cot in Colorado Springs, Colorado. That was their not as good version as I can get sexy, but still decent. So those are some Pythagorean identities which do come up. This one comes up least of all. This one comes up most of all. This one also comes up quite frequently, especially in 21B. These identities come up a lot when you're trying to integrate powers of trig functions. All right, I think that's all I feel like I need to say about trigonometry for the moment. Let us move along to inverse functions. And yes, logarithms are also on that list. We're going to boil them in. Yeah. So, inverse functions. Useful for all sorts of things. Let's start off with some basic examples. Sorry, my paper looks very crooked. There we go. So let's say we have the function f of x equal to 3x plus 2. Yeah. I would love to know what the inverse function is. And for some functions that are kind of what I would think of as being straightforward, you can actually just kind of talk it out. So what does this function do? This function takes an input of x, first multiplies it by 3, then adds 2. The inverse function should undo those things. And to undo them, you really have to undo them in the opposite order. So to undo the addition by 2, I'm going to subtract 2. And then to undo the multiplication by 3, I'm going to divide by 3. So my inverse function should be, I'm going to take my input. I'm first going to subtract 2. I'm then going to divide the whole thing by 3. Now, is that like a good method to do it all the time? Definitely not. But if your function is linear, it's pretty not terrible to do it that way. Like it's not, are you going to get full credit for doing this on the exam? Probably not. You probably need to show your work, which we'll talk about in a minute here. But just for this example. So these two functions undo what the other one does. For example, f of 5 is 3 times 5 plus 2, which is 17. So f takes an input of 5, gives an output of 17. And the inverse function g undoes that. It interchanges the role of the input and the output, or the domain and the range. So g takes an input of 17, and 17 minus 2 is 15. 15 divided by 3 is 5, and gives an output of 5. And that, I really couldn't say it any better than I have. That is the nature of inverse functions. They undo each other. One of them does something to x, gives an output of y. The other one takes that output of y, uses it as the input to give you back an output of the x you started with. So what should always be true for inverse functions, in fact, kind of by definition here, f of x and g of x are inverses of each other. I guess it feels kind of unnecessary to write those parts, but whatever. If and only if, by the way, so if and only if means it's true both ways, meaning we say they're inverses if this thing is true, and if this thing is true, we say they're inverses. And mathematicians, being super lazy all the time, would always like to write less things than they have to. So we abbreviate the words if and only if with the letters IFF. So if means if and only if. Meaning that both implications are true. If the first thing is true, then you can conclude the second thing is true. Or if the second thing is true, you can conclude the first thing is true. So f of x and g of x are inverses of each other if and only if both f of g of x is equal to x and g of f of x is equal to x. And it is important to check both. There are notable exceptions where it works one way and it does not work the other way. We'll talk about a couple of those because they actually are super important when talking about the inverse trig functions. In this case, totally works, right? If we find f of g of x, it's equal to f of x minus 2 over 3, which is then we plug in that to that. So it's 3 times x minus 2 over 3 plus 2. The 3's cancel. You get x minus 2 plus 2. The 2's cancel. You get x. I also say the 2's add to 0. The 3's divide to 1. Canceling is a bad word. Canceling is a bad word in math, because it's just so, it's not specific, right? When I say things cancel, well, sometimes we mean 3 divided by 3 is 1 and the 3's cancel. Sometimes we mean negative 2 plus 2 adds to 0 and the 2's cancel. So I should be more specific about what I mean when I say I'm canceling things. But I only check one direction, so I should check the other direction. So g of f of x is equal to g of 3x plus 2. That's equal to g, not g of, I'm actually g. So g is x minus 2 over 3. So g of some stuff is the stuff minus 2 over 3. And I'm just going to plug in what's in the parentheses there. And get 2 minus 2 is 0. So 3x divided by 3. And then 3 divided by 3 is 1. So I get 1x, which is just x. Check. It works. They're inverses. If two functions are inverses, we usually call the other function f inverse. So we would call g of x by the name f inverse of x. We do not say f to the negative 1 of x. We say f inverse of x. That is the correct and really only way you should say it. Notably, it is not the reciprocal. Except for okay, I should point out, there are 3 rare functions where the inverse does happen to be the reciprocal of the function. But in general, not right. These are obviously not reciprocals of each other. So, right, superscript negative 1 doesn't always mean 1 over. Sometimes, a lot of times it does. In the inverse function section of things, it does not mean that. So, how do you find an inverse? There's a couple ways. Let's look at an example sure. Let's say we have the function 2x to the third plus 7. And we would love to find the inverse. And this is one I would also argue you could talk out or just kind of figure out how to undo the operations in the opposite order. But we're not. We're going to use a method. So it's a 4-step method where really only one of the steps you're actually doing anything. So first step, replace your function with the letter y. Second step, interchange x and y. So your only y should become an x, and all of your x's, which there might be more than one of, become y's. So far, these steps we haven't really done much. Although I will say the second step is vital here because that's the step where you're actually literally interchanging the role of x and y. And now, step 3, the step where you actually have to do some work, solve for y. Some people prefer to do the solving first and then the interchanging second. I don't, but you don't have to do it the same way I do. So you can solve for x first and then interchange x and y if that feels better to you. So solve for y. So let's see, subtract 7 from both sides. Divide both sides by 2. And then take the cube root of both sides. I will point out, finding the inverse function really depends heavily on your ability to know the order of operations correctly, right? What things you have to do before you do other things. So cube root both sides, and you get the cube root of x minus 7 over 2 is equal to y. Or if you prefer, y equal to x minus 7 over 2 to the 1/3 power. Equivalent statements, expressions. So the last step, also kind of a non-step, but I'm going to write it anyway. We rewrite it as f inverse of x equal to the cube root of x minus 7 over 2. that's the process for finding an inverse function. I'm trying to think of a good example here so we can see some graphical things that are interesting, but yeah, we'll get there. Okay. We've got two more examples, I think, and then we'll kind of switch back around to a couple more examples. Questions about this one before we do another one, which will exhibit some other facts about inverse functions. It is okay to ask questions. It's also okay not to have them. Like maybe this is all I know. So people are in different places, right? This might be like, yeah, I've seen this a million times, or maybe like this is like the first time I've seen this. So it's really okay to be in different spots. We're all trying to get the same spot, which is through calculus. So let's look at another example, which is one of my favorites. So let's say our function was, let's do that, 3x minus 7 over x plus 2. And before we find the inverse, one point of interest here, let's talk about the domain. So here the domain, well, if I was doing this kind of the standard way, I would say, well, I don't have any roots, I don't have any logarithms, but I do have a quotient. I need to make sure I'm not dividing by 0. So I want to make sure I exclude where the denominator is equal to 0. So I want to exclude where x is equal to -2. So my domain here would be everything from -infinity to -2, union -2 for infinity. And we're not just talking about that because we should talk about domain. There's another reason which will become apparent in a little bit. All right, so let's go ahead and find the inverse function. This one's a little bit more work. It's kind of an added step. So we're going to first replace our function with the y. So we have y equal to 3x minus 7 divided by x plus 2. And then we're going to interchange. So our 1y becomes an x, and all of our x's become y's. So 3y minus 7 divided by y plus 2. So when you're finding the inverse function, when you're solving for y, there can't be y's in your answer. So a lot of times you see people like multiply both sides by y plus 2 and then add 7 and then divide by 3, and they're like y equals x times y plus 2 plus 7 divided. Oh wait, there's a y in my answer? That's not okay. So we have to first get all the y's to one side before we can isolate y. So I still want to get rid of my denominator, right? That's always the first step, I think, is to get, well, maybe not the first step, but it's often the first step is I don't want fractions. So we're going to multiply both sides by y plus 2. I don't think you need to write that on the right-hand side, right? You could write 3x minus 7 divided by y plus 2 times y plus 2, or you could just know that y plus 2 divided by y plus 2 is going to be 1. 3x minus 7, that's why we're doing it, so we don't have a fraction anymore. So we have, I'm going to distribute here, x times y plus x times 2 equal to 3x minus 7. And now we're going to group all the y terms on one side, sorry, now my brain's like, I made a mistake. You guys know what mistake I made? So here, before you say anything, I was saying I need to group all the y's on one side, but they already are. Yeah. Yeah, I accidentally, and that's an easy mistake to make, right? Y and x, unfortunately, kind of are similar, at least when I write them. So be careful here. That should be a 3y minus 7. That should be a 3y minus 7. Yeah. So now we're going to group all the y's on one side. It doesn't matter which side you pick, as long as all the y's are on one side and everything else is on the other side. I generally try to keep more things positive than not. So I'm going to bring my y's to the right so that this -7 can come over to the left as possible. But either choice is fine. So I'm going to say 3y minus xy on the right-hand side and 2x plus 7 on the left. Now that all my y's are on one side, and I'll do it the other way over here as well. Or if you like, where'd you go? Xy minus 3y on the left and -2x minus 7 on the right. In either case, whichever side has the y's on it, we're going to factor out y. So we're going to have 2x plus 7 equal to y times 3 minus x. Or if you went this way, y times x minus 3 equal to negative 2x minus 7. Finally, divide both sides by whatever is multiplying y over here. So 2x plus 7 divided by x minus 3 is equal to y. Oh, thank you. Or over here, y is equal to negative 2x minus 7 divided by x minus 3. Those are the same function. They just look slightly different. But if you took this function, making errors again. You guys see an error over here? I sure do. I'm supposed to divide by 3 minus x, not x minus 3. Jeez, 2 errors in one day. Inconceivable. So now both these functions are the same. If you took this function here and multiplied it by negative 1 over negative 1, you would get negative 2x minus 7 on top and negative 3 plus x on the bottom, which is the same as x minus 3. So they really are the same. Doesn't matter which way you write it. They're both equivalent. They're both good to go. So then finally, we can say that our inverse function, f inverse of x, is equal to 2x plus 7 over 3 minus x. And I will ask, what value of x is not in the domain of this function? Right. Yeah, 3. So notably here, our domain is everything but 3. Which I will then point out that if you look at your original function, 3 is the only number that's not in the range of the original function. Let me show you, just so you really believe it. We could graph it. We could pull up decimals and graph it, but I'll just show you. So here's your original function. And here's the inverse over here, just to have it on the same page. And I promise you, I'll make good on my promise here. I promise you that 3 is not in the range of this function, meaning this function can't equal 3. Okay, prove it. So if I set it equal to 3, 3x minus, oh my God, 7 over x plus 2. If I set that equal to 3, I'm going to get 3x minus 7 equal to 3 times x plus 2. If I multiply that out, I get 3x minus 7 equal to 3x plus 6. And then the 3x's, if I subtract 3x from both sides, those go away. And I get negative 7 equal to 6, which is not true. So that can't be true. There's no way this could ever equal 3, right? Whatever value you pick, I'll write it this way as well. You could also write this as so first of all, everyone cool with that? Is that the same? What did I do in the numerator? I added 6 and subtracted 6. I didn't change anything. I just wrote it differently. But then I'm going to break this up as 3x plus 6 over x plus 2. And then minus 6 minus 7 is minus 13. Minus 13 over x plus 2. But 3x plus 6 over x plus 2 is really 3 times x plus 2 over x plus 2. And as long as x isn't negative 2, this is just 3 minus 13 over x plus 2. And you know what's also true? This part here, never equal to 0. As hard as you try, you can never make that equal to 0. So this whole thing could never equal 3. Because whatever value I pick for x, you'd get 3 minus a little bit, which is never going to be 3. All this to say, inverse functions, we shouldn't be surprised. So what's the first thing we do when we try to find the inverse function? Actually, what's the second thing we do when we try to find the inverse function? We switch x and y. But x is like the domain and y is like the range. So when you find an inverse function, you are literally interchanging the role of the domain and the range. So this function here, f of x equal to 3x minus 7 over x plus 2. The domain, I'm just going to write the easy way, is everything but negative 2. And the range is everything except for positive 3. And the inverse is exactly everything is flipped. The domain is everything except for x equal to 3. And the range is everything except for y equal to 2. And that is by design, right? That's not a coincidence at all. Whenever you find an inverse function, the domain and the range interchange. Question. Sorry, did I write the wrong thing? Yeah, I did. Apologies. The third mistake of the thing. Sorry. Is that what you had to say too?
So I was just sixes.
So I employed a trick. What I really did there was I took a shortcut for polynomial long division. So I wanted to write this as a fraction in a way that was convenient. So what I said to myself was, I know that 3 isn't an option. So I want to make the top look like 3 times the bottom. And I know that 3 times x plus 2 is equal to 3x plus 6. So I said, I want to get 3x plus 6 on top. So I made it happen. I said, well, if I add 6 and subtract 6, then I'll have 3x plus 6, but I also won't have changed the value. Right? This expression here is exactly the same as that. It just looks a little different, but it's totally the same because this plus 6 minus 6 would add up to 0. And then still have 3x minus 7. But really, the longer, more kind of algorithmic way of doing this is I could have also said, in fact, worthwhile, because polynomial division is a thing. I was really doing this. 3x minus 7 divided by x plus 2, and then x multiplied by 3 gives me 3x. 3 times x plus 2 is 3x plus 6. Subtract 3x minus 3x is 0. Negative 7 minus 6 is negative 13. So then 3x minus 7 divided by x plus 2 is equal to the quotient plus the remainder divided by the divisor. Same expression I have up here, which you can't see. Just a more kind of typical way of getting there. But I was trying to take a shortcut. And again, if the polynomial division is like, what is going on there? Don't sweat it for now. I mean, you will need to use polynomial division in 21B for sure. It probably won't come up here. But if it does, we'll certainly talk about it more. It's not too terrible. It's still a little terrible. So, 15 minutes left. All right, 15 minutes left? Yeah, okay. So back to what I was saying, the domain of f of x is equal to the range of f inverse of x, and vice versa. The range of f of x is equal to the domain of f inverse of x. Which seems reasonable considering the way you get there is by, again, interchanging x and y. Shouldn't be too terrible surprise. So that brings in then, I feel like it's a prime moment to talk about the logarithmic and exponential functions and how they're inverses of each other. So probably my favorite exponential function is f of x equal to 2 to the x. And when I graph this, I usually graph this one by plotting some points. For example, I'm going to pick some values of x. Some convenient values like 3, 2, 1, 0, negative 1, negative 2, negative 3. So 2 to the third just means 2 times 2 times 2, which is 8. 2 squared is 4. 2 to the first is 2. 2 to the 0th is 1. 2 to the negative 1 is 1 over 2 to the first. 2 to the negative 2 is 1 over 2 squared. And 2 to the negative third is 1 over 2 to the third, which is 1 over 8. And the more negative our exponent gets, the smaller, closer to 0 our output gets, but never equal to 0. Right? It just gets smaller and smaller and smaller. So graphically, what this function looks like is what I would describe as your typical exponential shape. Plotting some points here, 0, 1, 1, 2, 2, 4, 3, 8. I usually don't plot the points to the left, I just kind of like eyeball it because it gets small real fast. So there's your usual exponential function shape. And we have a domain of all real numbers. We have a range of all positive numbers. but not zero, not positive. So how about the inverse function? Well, what's nice about inverse functions is graphically, they're super easy to deal with sometimes. Because you can, again, literally just interchange x and y. So here I have the points, 3, 8, 2, 4, 1, 2, 0, 1. I don't want to do those other ones there. So I can just plot the inverse points. So instead of 0, 1, I'm going to plot 1, 0. Instead of 1, 2, I'm going to plot 2, 1. Instead of 2, 4, I'm going to plot 1, 2, 3, 4, 2. Instead of 3, 8, I'm going to plot 8, 3. Kind of. Sorry. And then instead of -1, 1/2, I'm going to plot 1/2, -1. And instead of -1/4, sorry, instead of -2, 1/4, I'm going to plot 1/4, -2. And the smaller the input gets, the more negative the output's going to get. And you might recognize that as looking like a logarithmic function. And the log, I don't know if this is actually true, but I feel like it's true, is that the logarithmic function kind of occurs naturally as the inverse to the exponential function. Someone said, like, I want a function that undoes what the exponential function does. Oh, let's call it the logarithm. So instead of writing y equals 2 to the x, we're going to interchange x and y. And then we're going to solve for y. But since there wasn't really like a way to solve for y, we just make up a new function. Say, okay, great, solve for y. Y equals, we're going to call it this, log base 2 of x. Where again, what this means is literally, this means the same as that. Sorry. So this just means 2 to the y power equals x. And that's exactly what this means here, 2 to the y power equals x. And graphically, I think we can see that the domain for our logarithmic function here, so for the inverse function, f inverse of x equal to log base 2 of x, the domain is all positive numbers. That's how we see that we actually do have a domain restriction when we have a logarithmic function, right? We have to have the input being greater than 0. And the range here, although it takes a really, really long time, this function does get infinitely large, right? There's no like, it doesn't ever like turn around or flatten out. It just gets bigger and bigger and bigger, albeit very, very slowly. The range of this function is all real numbers. I would point out, it is definitely worth knowing that I'm going to use some limit language here, even though we haven't talked about limits yet. As x gets really, really large, this function gets really, really large. So we would say, I'm just going to write it down. We would say that the limit as x approaches infinity of this logarithmic function is infinity, because as x gets big, the y values get big. And what I think is more interesting, as x approaches 0, what side of 0 am I approaching 0 from? Am I on the right side of 0 or the left side of 0 from over here? On the right side of 0. So as x approaches 0 from the right, meaning the side that's bigger than 0, it's not necessarily the positive side, it's just the right side of log base 2 of x, that function gets very, very, very negative. So we'd say it's negative. I know I'm introducing some notation before we've really talked about all the meanings of things, but it felt like a good time to do it. So we'll talk more about limits next time. Okay, cool. So logarithms and exponential functions are inverses of each other as long as they have the same base. So probably the most important example of exponential logarithmic functions that are inverses, or just in general, are f of x equal to e to the x, and f inverse of x equal to the log base e of x, which you're never going to write that way. You're really going to write it as the natural log of x. But they mean the same exact thing. There's nothing to get hung up about here. This is just an abbreviation. So that's how you should think of it. It's just an abbreviation. Just like log base 10 of x is abbreviated as log of x. It's again like the IFF, if and only if, it's just because we're lazy. I don't want to write 4 letters when I could write 2 letters. Because it comes up often, right? Log base 10 comes up often, right? Base 10 kind of world here. And the natural base E is kind of the most important base when it comes to logarithms, for reasons we will see in the future. Okay. So I wanted to point out 2 other things about inverse functions. One is that sometimes inverse functions aren't really inverse functions. The best example of this is probably f of x equal to x squared, and g of x equals the square root of x. Are these inverse functions that always undo each other? Kind of, but not really. Let me show you what I mean. F of 3 is 3 squared, which is 9. Cool. And g of 9 is the square root of 9, which is 3. Seems good. Until you try using a negative number. F of negative 4 is negative 4 squared, which is still positive 16. But g of 16 is the square root of 16, which is not negative 4. It's positive 4. Not even plus or minus 4. It is just straight up 4. So the issue here is we have some domain problems. And actually, if you compose these functions, well, it depends on which way you do it. F of g of x is f of the square root of x. I'll point out here that at this juncture, you know that x has to be greater than or equal to 0. You can't take the square root of a negative number. So right here, you're saying, okay, well, we're limited. X has to be non-negative. And then you get the square root of x squared, which does end up equaling whatever x is, but x had to be greater than or equal to 0 in the first place. In the other direction, we have even bigger problems. G of f of x is g of x squared. No restrictions so far, right? X could be anything, positive or negative. But then, if you take the square root of x squared, I think we talked about this last class, you're not so lucky. You don't just get x, you get the absolute value of x. Because if x is positive, great, your answer is positive. But if you input a negative number, you're still going to spit out a positive number, which is exactly what the absolute value function does. And you know what? That doesn't meet the definition. G of f of x doesn't equal x. It equals something else. So these functions are not inverses. Unless we do something. We can make it so they're inverses. The real problem here is that one of these functions is violating something that we need it to not violate. Specifically here, f of x equal to x squared. Oh, sorry, that looks terrible. Violates the horizontal line test. So f of x equal to x squared, you can either say it violates the horizontal line test, which means that its inverse wouldn't be a function, because if we just took y equal to x squared and then switched x and y, x equal to y squared violates what? Right. Exactly. Because when you interchange x and y, vertical lines become horizontal lines and vice versa. So if your original function is violating the horizontal line test, your inverse relationship is going to violate the vertical line test, meaning it's not a function, meaning they're not inverses because the second thing isn't a function. So not a function. Another way to say this is this function, or I should say, right, violates the horizontal vertical line test. Another way to say the exact same thing over here is that this function is not one-to-one. So it fails to be one-to-one, meaning that each y value has only one corresponding x input. And that certainly doesn't work. So if you draw a horizontal line corresponding to one y value, like y equal to 9, you get two different corresponding x values. Which means when you interchange them, your x equal to 9 is going to correspond to two different y values, which is a problem because one input can't give you two outputs and still be a function. So the solution is make the problematic function less. Restrict its domain to where it is passing the horizontal line test. So the way you make these functions inverses, you say, great, we're going to say that f of x equal to x squared is restricted to the domain of x being strictly greater than or equal to 0. I shouldn't have said strictly there, just greater than or equal to 0. If it was strictly, it'd be just greater than. So then your graph of that is a lovely one-to-one graph that passes the horizontal line test. And its inverse, well, again, I'm just switching x and y, so 1, 1 becomes 1, 1, 2, 4 becomes 4, 2. It looks like this. Oh, but that's exactly the square root function. Right now, if we interchange x and y equals x squared, x equals y squared, square root both sides. The square root of x equals the square root of y squared. But since we knew that y had to be positive to begin with, the square root of y squared is just y. So we get exactly y equal to the square root of x. So here's your inverse function. So I would then say you do the same thing for trig functions, meaning I got 1 minute. So just for the quickest example ever, if I want to find the inverse of the sine function, ooh, that's the best drawing I've ever done. Not really. So there's your sine function, which is very, very not one-to-one, like almost as not one-to-one as you can be, because there's literally an infinite number of points it would cross if you drew a horizontal line between -1 and 1. So what we do is we restrict its domain for sine from -π/2 to π/2. And then the inverse function, right? If you just switch x and y, you get something silly. Right, here's x equal to sine of y, looking like sine. I'm going a little bit faster. We'll talk more about this next class for sure on Tuesday, for sure, like he says, and then it's like maybe not. But this is what the sine function would look like. Ooh, okay, come on, like that kind of. Clearly not a function. I should say this, the inverse relationship. But then if we limit ourselves to just living between here and here, which is from here to there, then you have the inverse function. So I'll graph it just so you can see it. Here's the inverse sine of x, which we write like this, or as this, the arc sine of x, which is my preferred notation because you don't have the potential mishap of thinking it's 1/sine, which is definitely not. Looks like this. It's got a very limited domain from -1 to 1. It's got a very limited range from -π/2 to π/2. And I wrote that π/2 in the exact wrong spot. Sorry. It looks like that. Looks like just a little portion of the sine graph flipped along the line y equals x. Similar thing is true for inverse cosine. The other inverse trig functions, inverse tangent, inverse cotangent, and inverse secant and inverse cosecant, are a little bit more intense. But that's the idea with the inverse trig functions. And then, no, I'll stop there. I'll stop saying things at 2:31. We'll talk more about it on Tuesday, and I imagine we'll start talking about limits because that's what's coming up next.